Hello, I am Deepoo Kumar. I would like to thank GTT for this opportunity to present our work on the dynamic modeling of BOF process using FactSage macro. This work is done by Vijay Kumar Chauhan, who is a master student, and me and Professor Jonathan are his guides. The content is quite straightforward. I will start with a very brief discussion about the BOF and the dynamic model, then the fundamental of this modeling approach, and the initial work that was done by student essential to learn this aspect, and our current model architecture, followed by some initial results and learnings. So this is the BOF steelmaking process. The primary function is to refine the hot metal, which contains impurities such as carbon, silicon, manganese, and phosphorus. So you can see the converter here, a schematic of that, in which what we essentially have is you first charge the scrap, hot metal, etc., followed by oxygen blowing, and then for about 12 to 15 minutes, then sampling and temperature to make sure the product is right, and if required, there's reblow, followed by tapping, and again slag splashing is optional to protect refractories. So now if you look at the process, the main part is this blowing aspect, which we are going to focus on in this model, which is for about 12 to 15 minutes. In this blowing process, there is a generation of emulsion, which we'll look at in a little more detail later on, and how to model these reactions we'll also see. Just to give you a flavor of what we mean by dynamic model, so essentially such models predict the change in compositions and temperatures, etc., of the system. So for example, here you can see a typical result from this reference. So this is carbon concentration change with respect to time. Here you have manganese, silicon, and phosphorus. You can see that the carbon and silicon has reasonable agreement. However, phosphorus is always quite tricky to model in the BOF process, whether you are using static or dynamic model. Such model can also predict the change in slag compositions as shown here in the right side. Slag compositions, of course, get affected by the oxidation of metal plus injection of fluxes such as lime and dolomite and so on. So the objective of the current work is to use FactSage macro to develop a dynamic model for the BOF process. The results that was shown in the previous slide was from the model developed earlier by Professor Balal, etc., at IIT Bombay. But in those works, pre-energy minimization was done using MATLAB instead of software like FactSage. So in this work, we are planning to develop further and use FactSage macro for doing the equivalent calculations wherever required. The model should predict the metal, slag, and gas composition with time and their temperatures during the blow with varying process parameters. And of course, one of the use of such a model is to find appropriate model parameters for given process conditions. So the current approach is quite simple in the sense that we start with the examples that is already provided in the FactSage called simplified BOF process. In that, you can see there are three sort of reactors or steps that are involved in this process. So what we have essentially in that example is liquid iron, and then we have slag. So there's flux injection and the oxygen injection. So what you see here are essentially three reactors, or what we have is in the reactor one is the metal, slag, and oxygen that will react, and then you have some output of that. So the reactant metal must go and homogenize with the bulk. So that is the R2, and similarly the slag product plus the flux injected should also react and give you the slag composition, which will have both liquid slag and some solids. That is essentially modeled by R3. In this worked example, in fact, says the different percentages are attributed, and this is some sort of random to give some reasonable result. And when you develop an actual model, the main job is to calculate appropriate amount that would be calculated from the process parameters instead of having some reasonable number, etc., like that. In that example again, the key thing is that the reactions occur between phases at different temperatures. So for example, metal is at 1300, slag at 1300. These are initial slag composition, but then gas and fluxes are at room temperature. So to have this kind of reactions, one must use mixtures or streams. To do these kind of calculations, various streams are created and the various equilibrium files are created to deal with this such a heterogeneous system in terms of both composition and temperature. Process is considered under adiabatic conditions as well, so that temperatures etc. can be calculated. As you know that there are several exothermic reactions that occur, such as oxidation of silicon and carbon. Again, the first step by the student was to essentially reproduce the example. So you can see that on the right side, this is the results from the FactSage example provided in their worked out example file, and these are the results obtained by the student here. So you can see that there's successful implementation, at least the learning from the student on regarding this development. So what we can see here is one of the key features is that the slag temperature, if you look at the first, it decreases and then increases, and this decrease essentially is associated with the initial flux injection, which is at room temperature. Silicon decrease, if you look at this too, in the current work, it actually remains, the decrease is not as significant as expected. Even in the example by FactSage, the decrease should have been faster. That's what is typically seen in the plant, but the trend is bit slower, and which we'll look at it a little later in more detail. So that was just the worked out example. In this work, we are developing it further by incorporating several fundamentals and the process aspects. So for example, here we have now again, there are three reactor. This is again 3 reactor models, but please note that these reactors are totally different here. So the reactor or the vessel is divided in 3 parts. One is R1, which is the hot metal or the lower bath. R2, which is upper bath of the metal that gets affected by the oxygen jet. And then R3 is emulsion, which is essentially has all the components, slag, metal droplets, and the gas. So the first step is the interaction between this metal and the gas, and this interaction results in there are chemical interactions as well as physical interactions. Chemical interaction will generate slag such as FeO, silica, etc. The physical aspect of that will generate a lot of metal droplets, which will fly into this emulsion phase. Which again, as has been discussed in literature, they remain suspended in emulsion because of the CO evolution from the droplet. Then there is exchange between this R2 and R3 in the sense that the physically generated droplet is first transferred into emulsion, and the reacted droplet essentially falls down. So this has to be incorporated in the work. Then there is reaction in emulsion itself. So if you look at the emulsion, as I said, it is multi-phase system. So you have liquid metal droplets, you have liquid slag, you may have undissolved solids such as CaO, etc., or MgO, or calcium silicates. So there is a reaction in this system in the emulsion between metal and slag. So those are considered mass transfer controlled reaction between metal droplet and the slag. So appropriate mass transfer coefficients have to be taken. And finally, of course, there is this droplet falls, and ultimately then there is exchange between the R2 and R1. So some, let's say, fixed amount of metal gets from R2 to R1, and the same amount of metal gets from R1 to R2, so that the reaction continues, and then you have the chemistry can be calculated in different at different locations in the converter. This shows a little bit more detail on the model architecture for a single time step. So you have initialization of metal, slag, and streams in reactors 1, 2, and 3. These initializations of streams are done using appropriate equilibrium files. Then you have the metal gas reactions. Then you have droplet and slag transferred to R3 because of these metal gas reactions, as I discussed. You have physical interactions as well as chemical interactions. So you have droplet and slag that gets transferred to R3, which is the emulsion zone. And then in R3, you have emulsion reactions, which is essentially between metal droplet and the slag, which are mass transfer controlled. And then in R3, after these reactions are happened, have completed, then there is mixing of product within R3 itself, because the reacted slag and reacted metal has to get mixed with the droplet and the slag respectively. After that reaction, some fraction of the droplets will fall and come to R2, and then you'll have an updated chemistry and temperature of R2 because of that reaction. And finally, there is an exchange of metals between R1 and R2. And at the end of this one-time step, all these calculations, we update the chemistry of metals and slag, metals in R1 and R2, and R3, which is in the droplet form, and then R3 also with the slag. So as you can see here, the initial results are shown here. So we have the silicon composition with time, silicon with time, and then carbon with time. So here what we see are the three lines. So we have the composition in upper bath, and then composition in the lower bath, and then the average. As you can see, since upper bath is an active zone where you have the direct droplet generation plus the reaction with the gases, so the changes is much faster in the upper bath, which gets transferred to the lower bath because of this intermixing or exchange of metals between one and reactor 1 and reactor 2. So the center line, of course, gives the silicon content, change in silicon content with time. That is the average for both baths. Of course, this excludes the changes in the metal droplet that is there in the emulsion zone. On the right side, what we see is essentially the change in carbon composition or carbon concentration in again upper bath, lower bath, and then the average. So as usual, like the previous one, here what we see is the upper bath, the change is much faster than the lower bath, and the average composition is like this. So the carbon appears, if you look at the change in carbon concentration time, this appears quite reasonable, what you see in the textbook, etc. But the silicon is a bit puzzling, in the sense that what we expect is generally the silicon should decrease much rapidly at the early times, but this is not observed so far. So we need to look at it in detail. So this was also, as I pointed out earlier, even in the example file, if you look at the silicon decrease is not quite fast. What we have seen, and it's not shown here, is that the silicon decrease starts occurring only when there is good amount of FeO buildup in the slag. So this we need to look in little detail. So the learning so far is that setting up a stream and equilibrium properly is really important to make sure that you're selecting a adiabatic system to calculate the correct temperatures. You select the right solutions and species. And the other thing that we learned after many iterations is that FactSage macro gives error if the amount of first stream in the equilibrium file is 0. So you have to make sure that you set up a stream file such a way that this number is not 0. More practically speaking, if you are, let's say, having a reaction between metal and gas phase, which is in R2, sometimes you may generate solid silica, sometimes you may generate liquid slag in the sense of a few silica combined. And so one of those components may become 0, and that used to give us many times give us errors. So one needs to be careful about this thing. A desynchronization calculation, as I discussed in the previous slide, it seems erroneous. It needs further investigation. We need to look at if further debugging is required, or there's some database or solution or species selection issues. In the future, we would like to so far we have taken typical numbers for all the parameters, but now we would, going forward, once we correct for the silicon, we would like to incorporate primarily the oxygen blow, whether it's soft or hard blow, enhanced positions, droplet generations, etc. And then we would also like to study the effect of some model parameters that are really difficult to estimate, such as droplet resistance time, exchange rate between reactors 1 and 2, that is upper and lower bath, and the mass transfer coefficients. These are really difficult to estimate parameters, so we need to adjust and see what makes sense. With that, I would like to thank GTT again for this opportunity, and would like to acknowledge various sources for funding FactSage. And with that, thank you very much. I would welcome any questions during the interaction session. You can contact me at this email ID as well if you have any questions. Thank you.